Welcome back to part 24 of my DIY autonomous mobile robot building series. If you're just joining us, be sure to check out parts 1 through 23. The links are in the description and the full playlist is at the end of this video. For the remainder of the CAD design stage using Fusion 360, I'll focus more on what was done and why rather than showing every single step in detail. I'll still cover any new techniques, but this will help us maintain a steady pace as we move toward the physical build stage. Moving on from part 23, our first task is to increase the clearance at the front of the lid to accommodate its rotational movement when opening. Here the footage shows a sectional analysis being created through the center of the robot. To test the rotation of the lid, let's scroll down to the joint labeled rotational lid, right-click and select Animate Joint Relationships. This rotates the lid through its full range of motion. With the lid open slightly, you can see that there is virtually no clearance between the front of the lid and the lower body. To solve this, I created a cutting tool based on the existing lid tool geometry and used it to remove a small amount of material from the lower body at the front end of the lid opening. This increases the gap at the front edge of the lid while leaving the remainder of the perimeter unchanged. After applying the modification, the lid has noticeably more clearance at the front side compared to the other sides. Here is the before, and this is after the cutting operation. Now the lid can rotate smoothly without coming excessively close to the lower body. At this point, the footage jumps ahead. The lower body is hidden and we're ready to create a washer component for the hinge assembly. One Fusion 360 update worth mentioning here. This footage shows me selecting create and then new component. Since this was recorded, Autodesk has restructured the design workflow so that the command may now be located elsewhere, but the functionality remains exactly the same. Let's label the new component M2 washer 2.2 by 5.0 by 0.3. The 2.2 refers to the inner diameter, the 5.0 is the outer diameter, and the 0.3 is the thickness of the washer. The footage shows the washer being created as a simple ring-shaped component with a small edge fillet and a black appearance applied. Once complete, position the washer on one side of the hinge assembly using the joint tool. Then create a copy and place a second washer on the opposite side. Next, let's look at the rearmost connector tube. I wanted to add a rear latch to the underside of the lid that would fit neatly between the inner walls 1 and 2 and locate around the connector tube. Before doing that, I checked the available space between the inner walls and found it to be 26.4 millimeters. To provide some clearance, I shortened the connector tube slightly by editing the extrude operation in the timeline, reducing its length to 25.5 millimeters. Then I removed the fillets at the ends of the tube and added a curved tab at each lower end using the 3-point arc slot tool to act as a stopper for the lid when it closes. To create the curved slot, select the 3-point arc slot tool under slot in the create menu. Select the start of the arc, the end point, and a third point to define the curvature. Drag the slot width outward and snap it to the outer circle. Finally, fully constrain the sketch using the dimension tool and set the arc radius to 0.25 millimeters. I formed each curved tab based on this curved slot by extruding it out by 0.45 millimeters. Measuring the total length of the tube, including the curved tabs, gives us a length of 26.4 millimeters once again. Here, the rest of the design is unhidden, showing the modified tube in place with a gap at either end acting as a lid stopper. Next, I sketched a rear latch profile for the lid. Using the conic curve tool, I created a curved battery stay or stopper that helps keep the 9-volt battery steady when the lid is closed. I used the offset tool to give it a thickness of 0.5 millimeters. I created the rear bracket and the battery stay based on these profiles, and the extrusions look like this. With the lid unhidden, I used boundary fill to create an independent copy of it, then used the cut operation in the combine tool to remove the excess portions extending above the original lid. Then I combined the rear latch and the battery stay with the lid using the join operation in the combine tool. So there we have the lid rotating with the rear latch and the battery stay as a single integral component. Here's the rear view of the lid opening and closing. I hid battery pack rear hook 3 and inner wall wall 2 for better visibility, and as we can see, the rear latch of the lid interferes with the rear M3 bolt. To fix this, I created a sketch on a plane lying on the side of the rear latch, isolated the lid component, and sketched a 3mm circle corresponding to the M3 bolt. I then used the circle tool to create a curved track centered on the hinge, allowing the rear latch to smoothly engage with the M3 bolt without interference. Then I completed the design of the rear latch, removing any portions that would interfere with the curved track. That looks like a sturdy, reliable latch for the lid. Here we can see the relationship between the rear latch and the M3 bolt, with the latch securely engaging with the bolt to hold the lid closed. We can also see the rear latch engaging with the curved tab of the connector tube. I added a 6mm fillet at each lower corner of the battery stay. I also sketched out a brace or web to extend between the rear latch and the battery stay, extruded it down and through the lid, and cut off the excess. Upon removing the excess, I labeled the remaining body web. Upon rotating the lid, the rear latch, the battery stay, and the web integrally rotate as a single component. Here in the footage, inner wall 2, battery pack rear hook 3, and outer walls 1 and 2 are unhidden. It was at this stage that I realized I didn't have a long enough M2 bolt for the lid hinge, so I decided to use 2 separate shorter bolts, one for each side. I modified the design by reducing the length of each hinge spacer down to 3.2mm, then added an M2 washer on each inner side of the shortened hinge spacers. Let's measure the distance across the 2 washers, and we get a distance of 8.4mm. From the insert menu, I selected Insert McMaster Car Component and downloaded a 12mm M2 socket screw. I applied a chrome pigment, which is probably the most visible out of the metallic options, and used the joint tool to attach it to the hinge. Here's a cross-sectional view along the central axis of the 12mm M2 screw, and we can see that it does not interfere with the robot body. So I made a copy of the 12mm M2 screw and inserted it into the other hinge hole using the joint tool. I also downloaded an M2 nut, attached it to the end of the screw, made a copy, colored them chrome, and attached the copied nut to the other side. Unhiding the lid, we now have completed the entire lid assembly. It's time to divide the lower body into separate panels and work out how to attach them to the chassis. Here I have created a few spare copies of the lower body. The footage shows the lower body hidden, with only outer walls 1 and 2 visible. I want to be able to detachably mount the left and right sides of the robot body to the outer faces of outer walls 1 and 2, and also provide a means of detachably mounting other body panels. I created a new component, labeled it Body Cutting Tool, and started a sketch on the outer surface of outer wall 1. Starting from the origin, I sketched out the cutting tool and projected the entire face of outer wall 1. I unhid spare body 1 and projected the entire lower body, as we will need to cut in the horizontal direction as well. Then I sketched out the vertical profile of the cutting tool, removed some of the excess projected lines, finished the sketch for now, and hid spare body 1. I extruded the vertical profile by negative 0.5mm in a direction away from the outer face of outer wall 1. I also made a copy of this vertical cutting tool and positioned it onto the outer face of outer wall 2. Then, with spare body 1 unhidden, I edited the sketch to add the lateral horizontal cutting tool portions, one at the front and one at the back, each having a profile thickness of 0.5mm. After finishing the sketch, I extruded each horizontal profile by 73.3mm, which is the width between the 2 vertical cutting tools measured off camera. Later, I realized that the front lower portion of the vertical cutting tool needed to extend rearward more, so I edited the sketch accordingly and extruded that extra portion by negative 0.5mm as well. This is what the cutting tool looks like now, and this is its position relative to the lower body, which is spare body 1 in this instance. Lastly, we need to cut the upper part longitudinally into left and right central portions, so I created a new sketch on the YZ plane. I projected the entire profile of the cutting tool, hid the body, and unhid spare body 1 for reference. Here's the profile of the central vertical cutting tool. With spare body 1 hidden again, I extruded the vertical cutting tool with the direction set set to symmetric so the extrude occurs evenly on either side of the central YZ plane. I didn't want much of a gap along the center, so I only extruded by 0.2 millimeters with the measurement set to whole length, making the extrusion just 0.1 millimeters on either side. Unhiding the rest of the cutting tool body, we have a completed cutting tool for the lower body. Unhide spare body 1 again, then I use the combine tool to cut spare body 1 into the various panels. I labeled them right panel, lower front panel, center right panel, left panel, and center left panel. Finally, I selected all these panel bodies and moved them into the lower body part component, removing the older testing bodies I was playing around with off camera. The footage now shows the central right panel and outer wall 2 unhidden. Let's turn it around to the inner side, create an offset plane on the inner face of outer wall 2, and move it inward by a clearance of 0.2 millimeters. Turning the design around, I'll hide outer wall 2 and create a new sketch on that offset plane. Here I sketched the basic profile of a wall part for the center right panel and extruded it as a new body by 0.5 millimeters. I labeled it tabs as I intended to create tabs for attaching the component to the chassis, but I ended up changing the design as we'll see later on. I used the boundary fill to create a copy of the center right panel to act as a cutting tool, and then used the combine tool to cut the wall part with this tool. After removing the excess, we can unhide the center right panel. Next, we have outer wall 2 unhidden, which I colored white for better visibility. Here's the right panel. Although the center right panel still needs some work, I decided to focus on the right panel first. With the right panel activated, I created a new sketch on a plane that lies on the outer face of outer wall 2 and projected its entire profile. I sketched a rectangle centered at the origin that extends outside the entire profile of outer wall 2. I finished the sketch and extruded the profile by 0.5 millimeters, leaving out the holes projected from outer wall 2. After unhiding the right panel, I used boundary fill to create a copy of it as a new body to act as a cutting tool. I hid the original right panel, renaming the newly created body 3 to tool and body 2 to 0.5 millimeter wall. After using the combine tool to cut out the newly formed wall, I realized that the bottom wasn't completely cut out due to the shape of the right panel. Off camera, I sketched 2 parallel lines and used the extrude tool to finish the cut. Here's the cutout wall with the right panel unhidden. My next challenge was working out how to attach this component to the outer wall. Let's turn the wall around so that we are facing it from the outer side. I filled in the rectangular holes in the wall using the join operation of the extrude tool and extruded them by 0.5 millimeters. Initially, I designed the walls of the left and right panels to fit over the M3 bolts and the HS311 servos, resting against outer walls 1 and 2, where they would be slid horizontally forward into position. However, much later, after I thought I had completed the design and built the robot up to this stage, I realized that it was impossible to slide the left and right panels without them interfering with the 2 front M3 bolts and the wheels. Because of this, I had to change the design of the left and right panels, as well as the cutouts in the 0.5 millimeter walls. I will show you how I successfully modified the design in a future video of this series. As you can see in the footage, I created a 4 millimeter diameter circle at a random location, placed it at a lower position on the upper component of battery pack rear hook 3, and constrained it using the dimension tool so that it centers 0.5 millimeters from the lower side and 18 millimeters from the front hole. I also sketched a 2 millimeter diameter hole inside it. After finishing the sketch, I extruded the boss I created by 3.7 millimeters and formed a thread inside the hole using the thread tool. With one M2 screw hole done, I downloaded the M2 screw from McMaster Car, added a chrome pigment, and renamed it M2 Phillips screw 20 millimeters. However, I didn't want the thread of the screw to go right up to the head, as I wanted the screw to connect with a keyhole slot. Using split body, I selected the entire screw as the body to split, and selected the face on the underside of the head as the splitting tool to cut straight through. Then I used an offset plane 1 millimeter from the underside of the head and split the thread again. I removed the cut body between the planes and extruded a cylindrical body using the join operation configuration, which automatically joins the head, the 1mm cylinder, and the thread into a single integral body. Next, I inserted this modified screw into the hole we just formed in the upper component of battery pack rear hook 3 using the joint tool, positioning the underside of the head 20.25mm minus 3.7mm, the thickness of the upper component, from the outer face of this component. Unhide outer wall 2 and let's look from the top view. Here we can see there is enough room for a keyhole formed in the 0.5mm wall to slide along the smooth cylindrical portion of this screw. I initially created a keyhole in the 0.5mm wall, but because I had to change the design of that keyhole later, I won't go into details here. By the way, this is the other end of the M2 screw, which sits almost flush with the inner face of the upper component of battery pack rear hook 3. I also ended up increasing the size of the boss supporting the M2 screw from an outer diameter of 4mm to 5mm. This adds a bit more strength to the boss while utilizing the available gap between the two connector blocks of the Arduino Uno. The next thing I did was to extend the mounting tabs of the SG90 base so that they abut against the inner face of each 0.5mm wall of the central left and right panels. Click here for part 25. If the link isn't showing up yet, part 25 isn't quite ready, but should be ready soon. Be sure to check the description for my upload schedule. Thank you for watching.